Have you ever looked up at the night sky and wondered about those twinkling lights? Those are planets, our cosmic neighbors, taking part in a cosmic dance around the sun. For centuries, people believed that these celestial bodies moved in perfect circles. It seemed intuitive, harmonious, even perfect. However, the universe dances to a different tune. It wasn't until the 17th century that Johannes Kepler, a German astronomer, revolutionized our understanding of planetary motion. Through meticulous observation and groundbreaking analysis, Kepler revealed three fundamental laws governing the movement of planets. These laws, known as Kepler's laws of planetary motion, shattered the long-held belief in circular orbits and revealed a more complex yet elegant reality. Planets move in ellipses. Buckle up, because we're about to embark on a thrilling journey through the cosmos, exploring the fascinating world of Kepler's laws and the mysteries of elliptical orbits. Kepler's first law, also known as the law of ellipses, says that every planet's orbit is an ellipse, with the Sun at one of the two foci. This law was a radical departure from the popular belief in circular orbits. Imagine a circle stretched out like someone squished it a little, that's an ellipse. But what exactly is a focus, you ask? Think of it as a special point inside the ellipse. In the case of planetary orbits, the Sun occupies one of these foci, while the other focus is empty. This means a planet's distance from the Sun isn't fixed as it orbits. Instead, it gets closer and farther at different points in its journey. To really appreciate Kepler's first law, we need to dive a little deeper into the geometry of ellipses. Unlike circles, which have a constant radius from their center, ellipses have two defining parameters, the semi-major axis and the eccentricity. The semi-major axis is like the average distance between a planet and the Sun. Think of it as the long radius of our squashed circle. Eccentricity, on the other hand, measures how squashed our ellipse is. An eccentricity of 0 means we have a perfect circle, while an eccentricity close to 1 means a very long ellipse. Now here's the kicker. The eccentricity of planetary orbits in our solar system is relatively small. This means that even though they are technically ellipses, they are pretty close to being circles. That's why for a long time people thought they actually perfect circles. Kepler's second law, also known as the law of equal areas, describes how fast a planet moves in its elliptical orbit. It says that a line joining a planet and the Sun sweeps out equal areas during equal amounts of time. This might sound a little abstract, so let's break it down. Imagine a planet moving in its elliptical orbit around the Sun. As it moves, we can draw an imaginary line connecting the planet to the Sun. Now if we track the area this line sweeps out over a specific amount of time, like a month, we'll see that it's always the same no matter where the planet is in its orbit. This means that when the planet is closer to the Sun, it has to move faster to cover more ground and sweep out the same area as when it's farther away and moving slower. Think of it like a cosmic dance, with the planet speeding up and slowing down in a precise choreography dictated by the Sun's gravity. Part 5. Visualizing Kepler's second law sweeping through space. To help visualize Kepler's second law, imagine a pizza cut into equal slices. Each slice represents the area swept out by the line connecting the planet to the Sun in the same amount of time. Let's say the planet takes 1 month to travel through each slice. When the planet is closer to the Sun, the pizza slice is wider but shorter because the planet is moving faster. When the planet is farther from the Sun, the pizza slice is narrower but longer because the planet is moving slower. No matter where the planet is in its orbit, it will always sweep out 1 pizza slice, or 1 unit of area, each month. Part 6. Kepler's third law, harmony in the cosmos. Kepler's third law, also known as the law of harmony, shows the amazing relationship between a planet's orbital period and its average distance from the Sun. It says that the square of a planet's orbital period is proportional to the cube of its orbit's semi-major axis. Simply put, this means the farther a planet is from the Sun, the longer it takes to complete one orbit. What's more, this relationship isn't random, it follows a precise mathematical formula. This law highlights the basic order and predictability that governs the seemingly chaotic dance of the planets in our solar system. Part 7. Angular velocity, a new perspective on planetary motion. Now let's talk about another important idea, angular velocity. When we talk about planets moving, angular velocity means how fast a planet sweeps out an angle as it goes around the sun. Imagine a line from the planet to the sun. Angular velocity is like how fast that line spins. Here's the cool part. A planet's speed changes throughout its orbit because of Kepler's second law, but its angular velocity stays the same. This means even though a planet slows down when it's farther from the sun, it covers the same angle in the same amount of time. Understanding angular velocity helps explain why some planets, like Mars, sometimes seem to move backward in the sky. This apparent backward motion, called retrograde motion, is an illusion caused by Earth passing Mars in its orbit, just like passing a slower car on the highway. Part 8. Simulating the universe. Bringing Kepler's laws to life. Today we have sophisticated computer simulations that beautifully illustrate Kepler's laws. These simulations allow us to visualize the complex dance of the planets in our solar system and beyond. They accurately depict the elliptical orbits, changing speeds, and precise mathematical relationships described by Kepler's laws. Moreover, these simulations are not limited to our solar system. We can use them to model the motion of exoplanets, planets that orbit other stars, and gain a deeper understanding of the vast diversity of planetary systems in the universe. Part 9. Conclusion. Elliptical orbits, a key to understanding the universe. So, why are planetary orbits elliptical and not circular? The answer lies in the complex interplay of gravity and the initial conditions of the solar system's formation. When the solar system formed, the planets were born from a swirling disk of gas and dust. The gravitational interactions between these particles and the young sun led to the formation of planets in elliptical orbits. The discovery of elliptical orbits revolutionized our understanding of the universe. It challenged the long-held belief in perfect circular motion and paved the way for a more accurate and nuanced view of celestial mechanics. Kepler's laws not only explained the observed movements of the planets, but also laid the groundwork for Newton's law of universal gravitation, which elegantly describes the force responsible for this cosmic dance. Today, Kepler's laws remain essential tools for astronomers studying everything from the motion of planets and moons to the behavior of stars and distant galaxies, reminding us that even in the vastness of space, there is an underlying order and beauty waiting to be discovered.